Welcome to the Solutions Part 2 Screencast for Chem 1B at Shasta College. In the previous screencast, we saw that when a non-volatile solute such as sodium chloride is added to a solvent such as water, the resulting solution has a freezing point that is lower than the freezing point of the pure solvent. Now, when a solute is added to a solvent, the boiling point of the resulting solution is different as well, but it's actually higher rather than lower than the boiling point of the solvent. So, when a non-volatile solute is added to a solvent, the boiling point of the solution goes up. It's higher compared to the boiling point of the pure solvent, and the relationship should look very familiar to you. But there's a couple differences. So, the difference in temperature between the boiling point of the solution and the boiling point of the solvent is represented by delta T, and we have a subscript B to indicate it's a difference in boiling points. And that is proportional to the molality of the solution, but the constant of proportionality is a boiling point constant, represented by K sub B for boiling point, and then there's a Van 't Hoff factor as well. So this should look exactly like the freezing point depression equation, except it's B for boiling rather than F for freezing with respect to the delta T and the K. The boiling point constant is a different value than the freezing point constant, and the freezing point goes down, whereas the boiling point goes up. All the rest of it is pretty much the same. So solving boiling point elevation problems is very, very similar to solving freezing point depression problems, but you have to pay attention to use a boiling point constant, not a freezing point constant, and note that the solution has higher boiling point and the solution has lower freezing point. Now, why is the boiling point of a solution higher than that of a pure solvent? And for that matter, why is the freezing point lower? Well, we will look at the reason for the boiling point going up, and somewhat similar reasons apply for freezing point going down, but it's a little bit more sophisticated of an argument for that. And so for the purposes of this course, we will simply restrict ourselves to the reasons for boiling point increase. Now, when we have a pure solvent, so here we have blue spheres representing solvent molecules, and that's all we've got. It's 100% solvent. Above the solvent, there's going to be some molecules that were liquid molecules that overcame their intermolecular forces and escaped into the gas phase, and they exert a pressure, which is called the vapor pressure of that solvent at that temperature. So at a given temperature, a fraction of the molecules have enough energy to become gas. The fraction of the molecules with that enough energy depends upon what particular solvent we're dealing with and what temperature we are at. Now, if we instead have a solution, so here we're having red spheres represent solute molecules, and notice that in the solution, we have not 100% solvent. We have maybe 90% or some other value. Typically it's pretty high, but it's not 100% of solvent molecules, and a usually much smaller percent of solute molecules. And we'll still have a vapor pressure due to escaping gas molecules that came from the liquid, but they're, in this case, all going to be solvent molecules, because we're dealing with a non-volatile solute, and that means that the solute molecules, or ions if they might be that, don't form a gas. And note, we're going to have a lower vapor pressure over the solution because not 100% of the molecules are solvent that can escape and form gas. A smaller percent are solvent that can escape and form gas. So because we have a smaller concentration of solvent molecules, i.e. less than 100%, at a given temperature, we're going to have a smaller fraction of the solution molecules that can escape to become gas, and that's going to reduce the pressure, the vapor pressure above the solution by comparison to that for the pure solvent. If we compare the vapor pressure curve for a pure solvent to the vapor pressure curve for a solution when solute is added to it, and here we'll use the example of water. So this is the vapor pressure curve for pure water, and when we add solute to it and make a solution, the vapor pressure curve is displaced downward and to the right, and that's because the vapor pressure of a solution is lower at all temperatures than the vapor pressure of the corresponding pure solvent. And what that means is, now if we remember about what's required for boiling, at normal sea level conditions, normal conditions, we need the vapor pressure of the either, in this case, pure water, the solvent, or in the case of the solution, the vapor pressure of the solution. We need that to reach the 1 atmosphere in order for boiling to occur. And for water, the pure solvent, that's at about 100 degrees. But to reach a vapor pressure of 1 atmosphere for the solution requires us to go to a higher temperature. And so the boiling point, we would say, is raised or elevated because the vapor pressure of the solution is lower than the vapor pressure of the solvent, and a higher temperature is needed to reach the same vapor pressure as we had for water or whatever the solvent is for boiling to occur. So when a non-volatile solute is added to a solvent, the vapor pressure decreases, and that's what, in a sense, causes the boiling point to increase. Now, if we have a larger amount of solute added, a higher concentration of solute, then the solution's vapor pressure curve shifts even farther downward or to the right, which corresponds to an even bigger change in vapor pressure and an even bigger change in boiling point. So how much the vapor pressure decreases turns out to depend upon concentration, and the relationship is given by the following formula. P solution is equal to P solvent times X solvent or chi solvent, which is the mole fraction. So note that the mole fraction of the solvent is the number of moles of solvent over the number of moles total, which is moles of solvent plus moles of solute. And we can determine vapor pressure of solution if we know the vapor pressure of the pure solvent, and then it is going to be less because the mole fraction of the solvent will be less than 1, and this relationship is known as Raoult's law. So let's look at a little bit of this conceptually and then do an example. So graphically, if we go back to the equation relationship here, we have the vapor pressure of a solvent is a constant value at a particular temperature. And the mole fraction could change depending upon how much solute is added, and that will in turn affect the solution's vapor pressure. So mole fraction and solution vapor pressure are in fact directly proportional. That looks like this graphically. As the mole fraction increases, the vapor pressure of the solution increases. And if we sort of look at this in terms of kind of a conceptual understanding and let maybe red spheres represent solvent and a little red square here and yellow square represent amount of solute, then if we are at a mole fraction of 1, that's basically, and note this is mole fraction of solvent, that's basically 100% solvent. And so it's going to have a vapor pressure that's the vapor pressure of the pure solvent, because it is pure solvent. But if we have a mole fraction of 0.75, that corresponds to having 75% of the solution on the basis of moles being solvent. So here 75% is red, 25% is yellow. And what that means is the vapor pressure of the solution is 75% as much as the vapor pressure of the pure solvent. Same idea for 50%. If it's 50% solvent molecules, then you have 50% of the vapor pressure. If you have 25% solvent molecules by moles, then you have 25% of the vapor pressure. And if you had all solute, which is non-volatile, then there'd be 0 vapor pressure. So that's the relationship, kind of conceptual understanding type of idea. So example 7 asks us to determine the vapor pressure of a solution made by adding 38.7 grams of calcium chloride to 235 milliliters of water at 50 degrees Celsius. And note, these are the same values for calcium chloride and water as we saw in the freezing point depression problem in the previous screencast. The difference is we're now dealing with the solution at 50 degrees Celsius. So, how we determine the vapor pressure of a solution is we know that it is equal to the vapor pressure of the pure solvent, which in this case is water, times the mole fraction of the solvent, which is water, and the mole fraction of water is equal to moles of water over moles total, which is moles of water plus moles of calcium chloride. So, to solve this problem, we're going to need to calculate mole fraction, multiply it by the vapor pressure of water, and at 50 degrees Celsius, the vapor pressure of water is equal to 92.5 millimeters of mercury, and this is a lookupable known number which is needed to solve this problem. So we'll go ahead and calculate vapor pressure of solution equals pressure of water, which is 92.5 millimeters of mercury. And there's no particular unit necessarily needed here. We can use whatever unit we want for pressure. We'll just stay with the one we were given. And then we multiply that by the mole fraction of water. And notice we already know the moles of calcium chloride from the previous problem, but we are going to have to calculate the number of moles of water, and 235 milliliters of water is about 235 grams of water. Water is about 18.02 grams per mole, and that works out to be about 13.0 moles of water. So we have 13.0 moles of water over 13.0 moles plus the 0 point turned out to be 349 was the number of moles of calcium chloride from the problem in the previous screencast, and this works out to be 92.5 millimeters of mercury times a mole fraction of 0.974. Notice no units because moles cancel. And we therefore have a vapor pressure of the solution of 90.1 millimeters of mercury. And if you think about it a little bit, that seems fairly reasonable. The vapor pressure of the solution is a little lower than the vapor pressure of the pure solvent, and the solution is 97.4% on the basis of moles solvent, so the vapor pressure of the solution is 97.4% of the vapor pressure of the pure solvent, so that seems reasonable. And that is the end of Screencast 2. Stay tuned for Screencast 3.